Okay. Hello everyone. Welcome to today's session. Uh, yeah. Today, so this is week 8, and today we are going to solve network flow problem. So I have already shared the problem link with you in the chat box, and let me now share it on my screen. Yeah. So I think you must have gone through the problem already. So let me read it. So the problem is that a wedge is created by superimposing two squares. The bottom square should be of blue color and the top square should be of yellow color. The squares must be rotated in such a way that the projection of the wedge displays 8 distinguishable vertices. Please see following image for an example. In the picture, the leftmost configuration is permitted while the other two are not. You are given n squares, each of a given color and side length. Determine the maximum number of batches that you can make. Note that each square can be used for at most one batch. And the input format is that the first line of the input file contains integer n, which denotes the number of squares. Then the n lines contains two space separated integers ci and di. Ci is the color number, 1 for blue, 2 for yellow, and di is the length of the side of the square. And you have to output the maximum number of batches that can be made. And the constraints are that the number of squares is less than equal to 10 to the power 5, and the length is less than equal to 1000, and there are only two colors. And this is the sample input which we are given. So now I would like to know from you, what are your thoughts about the problem? Have you seen a similar problem in your course content?
No, it is kind of difficult. But what I have observed for first thing is that if you're trying to have a square, then the square that is made up of will both have a side length of equal, right? Because if they have if anyone has a lesser side length, then they won't like show the 8 distinguishable vertices we are talking about.
Yeah.
And therefore I think the flow network could be kind of making what square can overlap the other, and how with how much side length difference or so.
Right. Yeah. So first we need to create this graph because we are not directly given the graph. We are only given these numbers. As you have correctly pointed out, we need to find these edges. Basically, which two squares can be put together to form the wedge. Now I think so. There is one more detail in the problem, which is that the bottom square should be of blue color and the top square should be of yellow color. And so then can we put them like first without me saying anything, have you also seen some similar problem of this kind in your before?
Not a similar problem, but this is kind of showing that it could be a bipartite graph with like uh, source coming from going to the blue vertices, then blue vertices going to the yellow vertices, and then yellow vertices going to the target. The flow could be like that.
Right, right. Yeah. So then this is a bipartite matching, and our goal is to maximize the matching because we want to match as many blue squares with as many as possible to the yellow ones so as to create the maximum number of badges here. And right. So those are the two things which you have already correctly pointed out. So is it is the problem clear to everyone? And also you have correctly pointed, okay, great. So you have said that we can match. So what is then the condition to match a blue square to a yellow square, or vice versa, right? You know that. So only the first configuration is valid. The second one is not. When the yellow is completely inside, the blue is not valid. When the yellow is completely overlaps, the blue is also not valid. So then there is a mathematical condition, and can you guys tell me what is that? I mean, a relationship between the edge length of blue square and the yellow square.
And the edge length of blue square should be equal to the edge length of yellow square. That should be the condition.
Equal. Uh, not. I mean, okay. Think about it. If they are equal, then definitely this will hold. But if they are not equal, I think still it will hold, because the condition is that there should be 8 distinguishable vertices, which is also possible if they do not have equal.
Yes, ma'am. I think that would be the case if, like, there should not be like if any of those squares should not be the half of the other. Both should have kind of. I mean, let's say if there is a blue square of length L, then yellow should not be L by 2 or less. And similarly, if yellow is of L, the blue shouldn't be L by 2 or half less.
Okay. Okay. And what about others? Do you agree, or do you have some other opinion? Or is it clear to everyone?
Yes, ma'am.
Okay. Yeah. So I will share my screen. I mean, I could be wrong, but I think I thought it is a little different. So tell me. So this is my blue square. I think you can see. Okay. And let's say the edge length is 8. Now, if so I have this yellow square inside this. Okay. So in order for the yellow square to be completely, so that I can completely put it inside, the length of the yellow square edge, which let's say denote by B, I'll use red so that it is clearly visible. So then by the Pythagoras theorem, we'll have this will be a by 2, this will be a by 2, right, half, and then B is equal to a by 2 square plus a by 2 square and square root of that, which is basically a divided by square root 2. So B is, if B is equal to a divided by square root 2 or less, then it will completely be inside blue. But if it is greater than that, if it is strictly greater than a by square root 2, then it will slightly come out of blue and give us those 8 distinguishable edges, corners basically, not edges, I think those are corners. vertices. Yeah. So do you agree?
Yes, ma'am.
Okay. So then this gives us one condition, that the if I am matching a blue square of length A with the yellow square of length B, then B must be greater than A divided by square root 2. Now similarly there is other condition, which is so as to avoid the last case, that length of B must be less than some value. Now what is that value? So then we have blue square, okay, and we have this yellow one, and we are saying that the yellow is completely overlapping the blue one. My lines are not completely going to be correct.
That would be A root 2, I believe.
A,
Into root 2.
right? Yeah. So then this will be, if this is A, then this will be 8 times root 2 or root 2A. I don't know, like you can write both ways. So that is B. So then that gives us that B must be greater than A divided by root 2, less than A times root 2. This is the condition that we have. Now, given this condition, now that we know what's the condition, and if we are given these numbers, that is blue squares. So the input is here 10. There are 10 squares. First square is of length 3 and is of color blue. Okay. So then, as you already correctly pointed out, that we can form a bipartite graph in which the first set of nodes are blue squares and they will have their side lengths. We can represent each node by its side length, which is 3, 17, 10, 7, 8. And then the second other set of the vertices is the yellow squares. Then with the condition that we just discussed, we will connect these vertices and form this bipartite graph. Now the next step also, you have already correctly pointed out that now it reduces to the problem of finding maximum matching, which we have already studied in the course, maximum matching problem, and we know that we can solve this by using flows. So we have to add two vertices, S and T, and then we have to add edges from S to every blue vertex or blue square, and then similarly one edge from every yellow square to the to T, to the sink. And capacity of these edges, so what will be the capacity of these edges?
This is the problem. This is a place where I'm having the most doubt, but I think we can do it with just one pivot, just one, because like we're just we can use one square over the another square only. We cannot use one square with two of these, so we can just keep the weight as one, right? Yes.
Yeah. So we want to match a square with at most one other square. We cannot reuse. So therefore, we keep the capacity of the edges as 1, and then it reduces to finding maximum flow in this graph. So is this clear, or do I need to work out this example?
One more thing to verify.
Yeah.
Initially, when I looked at the problem, I also thought that we can like combine squares. Like, is that not possible? Like combining two or more squares to make a bigger one. But yeah, okay, we are trying to maximize, so we won't try to do that, I guess.
Yeah. Correct. No, okay. So I think what you said could be done, but the problem first line actually is saying a badge is created by superimposing 2 squares. So what you are saying actually can make a different problem, but this problem is saying only 2 squares are used.
Okay, actually, I missed that. Straight.
No, it's okay. Yeah. I also realized when you pointed out. So okay. So now we have discussed Edmund Karp's algorithm in class, and it works in, what's the time complexity?
That would be B squared.
Yeah, so the time complexity is order of VE square, and here we have n is equal to 10 to power 5. So then the constraints are very high for us to use Edmund Karp's algorithm. So we can't use it here. So we want a better algorithm. So I think Dinitz's algorithm has not been covered in the class. So I plan to cover that now using some resources, and so that then you can try similar problem. So this problem I'll share, you can code this as well, but there is another problem on sports, similar problem, which is matching. So the problem statement also we can look. Please ignore the add. So it says that there are
Just one more verification.
yeah.
In the problem statement, we are given that we can have around 10 raised to 5 vertices, like n is 10 raised to 5. So, won't they time out with the Dinix as well, because Dinix is d square, sorry, v square e.
Yeah. So yeah, the next time complexity is v square e, but on bipartite graph, it actually works in order of square root ve. So
Okay.
yeah,
Ma'am, in that case also e can be at max like
right,
e square, yeah, v square. So that would something be around
right.
v raised to, yeah.
Yeah, I understood that. So yeah, I think then Linux will also can also here not work if we have that many edges. Like if we have edges of the order of v square, I mean n square, then Linux will also not work here. So we then want the edges to be of the order of n actually. Otherwise, none of these algorithms work here.
That's why I thought it might. Can it be a mistake in the question, like n and d are replaced with the constraints that
Uh,
number of vertices is around 1000 and the length of one square could be around 10 raised to 5 or so.
it could be actually this. I really don't know. This problem statement is from the last year's course offering, so I do not know. and if there were any clarifications also made after the problem was released. But I am assuming that if these are the constraints and we have to, and since in this week we have only talked about max flow algorithms, so the best we have is DNX. And then maybe the test cases are designed such that the number of edges are not of the order of n square but of the order of n itself. Then DNX will work. Yeah, thanks for the question. But I like for example, this problem says that there are n cows, m bulls, where n is 50,000, m is also 50,000. Like similar to our case here, let's assume that 50,000 blue squares, 50,000 yellow squares, and then we are given a list of potential matches, which is here limited to 10 to power 5 only, like 1,50,000, right? So if we have similar constraint, although edges are not mentioned in our case, but if we had similar constraints, then DNX will work in this case. So you can try out this problem with DNX algorithm after this. Here also we need to find the greatest number of pairs. Okay. So
Yep.
yeah. So I have Anmilthara ma'am has pointed out this series by William Fissett, and it has really very nice. He has very nice resources and videos. So do take a look, or if you have not yet. So, and if you work with Java, then he has given source code in Java also. So now right now I am going to use his slides to explain the DNX algorithm. Okay. So in the time that we have, let us try to understand the DNX algorithm and also look at its implementation, then you can try to apply this algorithm on this forge problem that I have pointed to. So DNX is strongly polynomial. You can also go and check his video where he explains this. Okay. So DNX is a strongly polynomial maximum flow algorithm with a runtime of order v squared e, because it does not depend on the capacity of the flow, and in case of bipartite graph, it gives a time complexity of order square root v times e. Due to it, the algorithm's reduction to Hopcroft-Karp. Okay, and the intuition in DNX algorithm is that whenever you make a move, whenever you go from S, whenever you're taking the path, then try to take the path which is the shortest path to the sink. So that's also why Edmund Karp's works better, because it is using DFS. So here also it is like he has given this example. Let's say you want to go to a coffee shop and it is few streets away in east, then it only makes sense for you to head northeast, southeast or east, but does not make sense if you head in south or northwest. Okay, so this means that if you make in any direction which is in east, slight east, then you are guaranteed to make a positive progress towards the coffee shop. So this form of heuristic ensures that we continuously make progress towards whatever place of interest we desire to go. And now he asked that how can we apply this to solving maximum flow. So in this analogy, you are the source and the coffee shop is the sink, and the main idea behind the DNX algorithm is to guide augmenting paths from S to T using a level graph, and in doing so greatly reducing the runtime. So in Linux we form this level graph with BFS, where each level is same as the levels we have, that is the distance from the root, which is S in this case. Using BFS we form this level graph, and then we use this level graph to find the augmenting paths. Now we'll see the details of this. So the way Linux determines which edges make progress towards the sync T and which do not is by building a level graph. So here each color represents the different level. So red color is level 1, green is here level 2, and then the blue is level 3, and then we have the sync. And these levels are obtained by doing a BFS. Then furthermore, in this level graph, an edge is only part if it makes progress towards the sync. That is, the edge must go from a node at level L to a node at level L plus 1. So, for example, we have removed these edges which are between 1 and 1, this edge. We have removed back edges which were going from level 2 to 1. So we have an edge only which is going from a node at level L to another at level L plus 1. And the requirement that edges must go from L to L plus 1 prunes backwards and sideways edges. And if we are trying to, so the question here is actually, if we are trying to go from S to T as quickly as possible, then does it make sense to take the red edge going in the backward direction? So basically we are always, as it already talked like previously in a few slides back, that we want to always make progress towards the sync, and we want to do it as fast as possible because that is intuitive. So it does not make sense to take the backward direction edges unless we do not need to take them. So that's why those edges are not part of the level graph. If we are going from a level L plus 1, we cannot go back to L. So here it explains, now taking the red edge doesn't bring you closer to the sync, so it should only be taken if a detour is required. This is why backward edges are omitted in the level graph. Also stop me if it is not clear or if I am not explaining correctly. The same thing can be said about edges which cut across sideways to the sinks as no progress is being made. So these are the reasons why we always we are only including the edges which are going from L to L plus 1 in the graph, and actually omitting the edges which are either going back to some level, previous level, or which are on the same level. So it's also worth noting that residual edges can be made part of the level graph, but they must have a remaining capacity greater than 0. Okay, so you must have learned about residual, of course, in like Edmund Karp and Ford-Fulkerson algorithm. So these are these back edges that we add with capacity equal to the flow. So they can be part here of the, okay, I think it is talking about only the residual capacity, not the back edges. So that the residual capacity is nothing but the capacity, original capacity minus the flow. So if this is greater than 0, then they will be part of the level graph. Now the algorithm has 3 steps. First is construct a level graph by doing a BFS from the source to label all the levels of the current flow graph. Okay. Second step, if the sync was never reached while building the level graph, then stop and return the max flow. And third step, using only valid edges in the level graph, do multiple DFS from S to T until a blocking flow is reached, and sum over the bottleneck values of all the augmenting paths found to calculate the maximum flow. Now what's a blocking flow? A blocking flow means that you are not able to find any more augmenting paths. All the paths are saturated. So let's run through this example using the next algorithm to find the maximum flow. So here first we will construct the level graph. It's the same example. Then the level graph consists of only edges from LDL plus 1 which have remaining capacity greater than 0. Then we use the DFS algorithm to find the augmenting paths, okay, until a blocking flow is reached. That is, you cannot find any more paths. So this is the first path using DFS we found. And so when we find this path, we see that the bottleneck capacity here is 5. So we will then update the residual capacity of all the flow and residual capacity of all the edges in this path, which are updated like this. Where so the first value is actually representing the flow, and the value after the slash is representing the capacity. Okay, I should have cleared this before, but this is like this. So after this, so in this we have saturated the first edge from S to 1, and from 3 to T we have saturated these two edges. Next, so still we have some paths left in this, so the blocking flow has not been reached. So let's try to find the next path. So now this is the second path, and this path has blocking capacity, so the bottleneck capacity of 15, and then we update the residual capacity and flow in this manner. After that, we look for other augmenting path, and after this, there is no edge going from forward which can take us to T, and hence this is here we will terminate this iteration. So we are stuck, we can't find a path, so the blocking flow has reached. And now the residual graph that we have formed in the first iteration, we take that and then again apply BFS on it and construct the level graph. Okay, so rebuild the level graph. This time it should look different because the remaining capacities of multiple edges has changed. So when building the level graph, we only use the edges which have capacity, residual capacity greater than 0. So then if we form it, it will look something like this, and then we take all the edges which go from L to L plus 1 and have remaining capacity greater than 0. Then we again apply DFS on this and find a path from S to T. So now when we take this path denoted by blue arrows, then we reach 4, and after 4 we do not have an edge going forward. So it is a dead end. So we backtrack and again try to find. Now we have found this path, so we find the bottleneck capacity, update the flow values and the remaining capacities. And after this, since we have saturated the first edge which is going from S to 1, we cannot have any more augmenting paths, so the blocking flow has been reached and no more flow can be pushed. So the algorithm terminates here, and the maximum flow can be found by adding the flow of the edges which are running in T or the bottleneck values that we have seen during the different iterations of the algorithm, and this is equal to 30. So Here, one of the pitfalls of the current implementation of the DNX algorithm at the moment is that the algorithm may encounter multiple dead ends during the DFS phase. So, dead ends are highly undesirable because they extend the length of the journey from source to sink, especially if the same dead end is taken multiple times. So if we keep taking the same dead end again and again in different paths, then that is actually will increase the time we spend in finding the augmenting paths, and therefore some optimizations have been proposed to deal with it. And so Simon, Evan and Alan has suggested pruning dead ends when backtracking during the DFS phase. That we remove the dead ends, edges, and this greatly speeds up the algorithm because the dead ends are only encountered once and not again. So the summary of the algorithm is that we want to make progress continuously towards our goal, and that provides the speed. So we first construct a level graph using BFS, which directs the edges towards the sink. And in the next phase of the algorithm, we apply multiple DFS passes on the level graph until no augmenting paths are left. And then we rebuild the level graph from the graph that we got in the last pass. And then we again apply DFS, find the blocking flow, and in this manner we will keep continuing until we find the level graph, until we are not able to build a level graph. Okay, at that time we will terminate the algorithm. So yeah. And the critical optimization is to prune dead ends so that you do not encounter them again. So this is the DNX algorithm. DNX or DNX, both are used for this. And the time complexity is V square E. And in bipartite graphs, it works in order square root of V times E. Now I know if you have not looked at the algorithm before, some of the you may have some doubts. So are the main steps of the algorithm clear, or you want me please ask your doubts?
Just one thing. Like I was wondering, in the case where we like prune the edges or the paths that are like repeating again and again dead ends, then how would a BFS work on that instead of a DFS?
Yeah, so pruning pruning means we are saying that next time when we apply DFS, we don't want to go again to that dead end. So we do not necessarily have to remove that edge from the graph. We only need to keep that information somewhere so that we do not take those edges again. And that we can see in this implementation. So on this website CP algorithms, if you go to maximum flow DNX algorithm, you will find here the proof of correctness for this algorithm, and you will also find why the algorithm time complexity is order V square E. It also explains why the complexity is order square root V times E in case of unit network, which are like unit network, you can say bipartite is one type of unit network. So then you can go through these details, understand this. And now the implementation part is here, which let's try to understand that. Okay, and I will also answer, we can also see how they are taking care of these uh, like ignoring the dead ends, avoiding not taking them. Yeah, so this line, I think this is important. So it says a single DFS yeah, so let's read it from here, this paragraph. Not entirely, just this information is important, that in order to find the blocking flow on each iteration, we may simply try pushing flow with DFS from S to T in the layered network while it can be pushed. In order to do it more quickly, we must remove the edges which can't be used to push anymore. To do this, we can keep a pointer in each vertex which points to the next edge which can be used. So in each vertex, we are going to have pointers to the edges. So each vertex has a number of edges. So we are going to keep a pointer for every vertex which tell us that, okay, you have taken these edges. Now you need to take, this is the next edge that you can take. So keeping a pointer like this, I think, can help us in that optimization. We don't need to remove the edges from the graph, they are still there, but it also help us keep track of what edges we have already taken and do not need to take it again. Is this clear?
Yes.
Okay. It will be more clear with this implementation. So in the implementation, they have a struct flow edge, which represents the flow, which represents an edge, VU. Cap is the capacity, flow is the flow on that edge, and then we have one vector called edges, where every element is flow edge. Then we have a 2D vector of integer, we have a 2D vector where called adjacency, ADJ, and then we have n, I think n is the number of vertices, m ignore for now, s is the sink, s is the source, t is the sink, and then we have two more vector of integers here, level and pointer. So pointer is the one which is keeping track of the next edge to be visited, and q is used in the DFS algorithm. Now here we are calling this constructor on Dimic, and we are here resizing the ADJ vector, level vector, and pointer vector, and this is the add edge. Here this function adds an edge from VU with capacity cap. So it adds in edges. So edges is this vector of flow edge. So first it adds an edge V from V to U with capacity cap, and then it adds an edge, backward edge also, with from U to V with capacity 0. Okay, and then it pushes in the adjacency ADJV the position of this edge. So this edge, which is from V to U, so it is here adding that, inserting the position which is M, and M, then for U it is again adding M plus 1, and then M is modified to M plus is equal to 2, and M is initialized to 0. So that is how it is keeping this information. I hope this is clear. If not, then I think ma'am has also used similar structure in her videos. Then Here is the main method, which is flow. F is initialized to 0, and this is a while, infinite while loop. We run here, and then we first initialize. So level is an vector of integers, okay, denoting the level of every vertex. We initialize it to -1, then we set level of s is equal to 0, and then we push s in the queue, and then we run the BFS algorithm on it. So now when BFS runs on it, it will update the level of every vertex, and in the end it returns true or false. It returns true if the level of the sink was not equal to -1. If it is equal to -1 and BFS has ended, that means we are not able to construct a level graph which can reach the sink. Basically, sink is not reachable. So in that case, we will break if sink is not reachable. If it is reachable, then we come here. We here fill pointer from begin to end to 0, where pointer is also a vector of integer, and pointer is actually pointing to the next edge for every vertex that we want to visit. And as edges actually so edge are positioned, so that's why it's using this n here. So edges have a position in this vector edges. Then we call DFS. We pass here the source S and flow infinity. Okay, so this is being passed, so it will actually be updated throughout DFS with the bottleneck capacity. So in the end, it will give us the bottleneck capacity, and that will actually be pushed. So this will actually be then returned. This will be the bottleneck capacity, which we will add to our flow here, and then we will again do the DFS. So now if we look at DFS, so here we are passing first S and flow infinite, which is a very huge value, and it is actually a recursive code. So if it is saying that if pushed is equal to 0, that is if you are at a vertex V and you are getting the flow as 0, then we return 0. If you have reached at the sink, then you return the value of pushed, so that it can be added in the flow. Otherwise, you will find that edge using the pointer value, find that edge that you want to visit, and you're going to visit all the edges for V, but you're starting from pointer of V, and then basically you are first going to check if the edge is there in the level graph or not, and if the edge has a non-zero capacity or not. If the conditions are not satisfied, you continue. If the conditions are satisfied, then you basically jump to the next vertex, which is U, and you update the, this is important, you update the flow to minimum of pushed, which you are getting, comma, what is this, the capacity of this edge from V to U. Okay, because that much only you can push through this flow. And finally, when DFS returns, because it will return recursively from back, then you update these capacities, remaining capacities, residual capacities here, and return this variable tr. So this is, so it uses both BFS and DFS. BFS to construct the level graph, DFS to find the augmenting paths, and this is the algorithm Do you want me to explain again? Okay, so yeah, you can go back and then again look at this resource. You will definitely be able to find other implementations. This is but if you find this comfortable, you can use this or find some other implementation for Linux and try the problem on spot that I pointed you to. Try Linux on this and see if it works. I think the constraint, given these constraints, it should work. And if you also use the trick, which is optimizing by not repeating these dead end inches pruning technique trick basically, then I think that with that optimization should also help you. So that's all I had for today. I will also, you can also try this problem, and I will add some more sample test cases here so that you can try the correctness. You may not be able to try the time limit, like whether it passes that many test cases, but you can check the correctness. Do you have any questions? Did you understand the next algorithm? Okay. Anybody has any questions? No questions. Okay, then did you understand the algorithm?
No questions for right now.
Sorry, I can't hear you. Can
I said no questions right now.
okay. But did you understand the algorithm?
Yes.
Okay, good. Others, did you understand the algorithm? Or you may not have understood everything in the implementation, but the algorithm, the 3 steps that we discussed, do you have any questions in them? Okay, I assume that haven't been some questions, and everybody understood also. So then, okay, I'll share the resources. I think I've added in PDF here the link to the spot problem, the Linux algorithm YouTube video you can check from William, and William also has explain, like share the source code in Java. So also if you write code in Java, you can look at that. And if you write code in C++, then you can look at the algorithm implementation that we just discussed. Okay, then we can end the session and let's meet in next week. Thank you everyone for joining. Thank you.